Good morning, students. In today's class, we will start with the analysis of line-to-line fault on an unloaded generator through fault impedance. Line-to-line fault analysis on an unloaded generator through fault impedance. So let us consider a three-phase generator whose neutral point is grounded through a neutral impedance Zn. So this neutral impedance Zn is useful only for drawing the zero sequence network. A, B, C are the three lines or the three phases. Let IA, IB and IC be the currents through the three phases or the three lines. It's an unloaded generator, and let us assume the line-to-line fault occurs between the terminals of phase A, phase B and C. Okay, so we assume that the line-to-line fault occurs between the terminals B and C. Okay, so since it is through fault impedance, we consider a fault impedance ZF between the fault points B and C. So between the fault points B and C, we consider an impedance ZF. So now let us define the initial fault conditions at the terminals. So since it is the unloaded generator, there is no load connected at the terminals and the terminals will be left open. Okay, so there is no current flow path for this current IA. So we write IA is equal to 0. We write IA is equal to 0. Now VB is the voltage at point B and VC is the voltage at terminal C. So VB minus VC will be equal to the drop across the fault impedance. So the fault current IF will be equal to IB. So the drop across this impedance will be IB into ZF. So VB minus VC is equal to IB ZF, or we can write VB is equal to VC plus VB is equal to VC plus IB into ZF. And the third condition is current IB is equal to minus IC. Since IB and IC are along the opposite direction, we write IB is equal to minus IC. Okay. Now, next step is to draw the combined sequence network. So for drawing the combined sequence network, we need the relation between the sequence components of currents as well as the sequence components of voltages. So for that, we write the symmetrical components of current in terms of the current phasors. IA0, IA1, IA2 is equal to 1 by 3 into A matrix into IA, IB, IC. We substitute the initial terminal conditions for IA and IC. IA is equal to 0, IB kept as such, IC is equal to minus IB. Now expand. IA0 is equal to 1 by 3 into 0 plus IB minus IB, which is equal to 0. IA1 is equal to 1 by 3 into 0 plus IB minus, plus A into IB minus A square into IB. So IA0 is equal to 1 by 3 into 0 plus AIB minus A square IC. So IB is common. So 1 by 3 into A minus A square into IB. Okay. Now expand. IA2. IA2 is equal to 1 by 3 into 0 plus A square IB minus A IB. Okay. Again IB is common. We take IB outside, A square minus A. And since we have to arrive the relation between IA1 and IA2, we write A square minus AS minus of A minus A square. So IA2 becomes minus 1 by 3 A minus A square into IB, which is equal to minus IA1. So we have arrived at the relation between the sequence components of currents. Zero sequence current is 0. Negative sequence current is equal to minus of positive sequence current. Magnitude is same, but flows in the opposite direction. So now the symmetrical components of voltage in terms of the voltage phasors are given as VA0, VA1, VA2 is equal to 1 by 3 into A matrix into VA, VB, VC. Now VA1 equals 1 by 3 into VA plus A, VB plus A square VC. And VA2 is equal to 1 by 3 into VA plus A square VB plus A VC. Okay. So after writing VA1 and VA2 expressions, we are taking VA1 minus VA2 is equal to 1 by 3 into VA minus VA gets cancelled. A minus A square into VB plus A square minus A into VC. Okay. So leave this term as such. And A square minus A can be written as minus of A minus A square. Then again, this A minus A square is common in both the terms. So 1 by 3 into A minus A square into VB minus VC. So already in the initial terminal condition, we have, equation 1, we have proved that IA1 is equal to 1 by 3 into A minus A square into IB. Okay. So 1 by 3 into A minus A square into IB. Okay. So VA1 minus VA2 is equal to IA1 into ZF. Okay. So VB minus VC is substituted as IB into ZF from the initial fault at the terminals. Then from equation 1, these three terms we replace as IA1. Okay. Now, from the sequence networks of generator, we have this equation. VA0 is equal to minus Z0 into IA0. Since for line to line fault, IA0 is equal to 0, VA0 will also be equal to 0. So we have arrived at three important relations. First one is VA0 equal to 0, IA0 is equal to 0, which implies that the combined sequence network doesn't include zero sequence network. Okay, so VA0 is equal to 0, IA0 is equal to 0. So the combined network will not have the zero sequence network as shown in this network. Okay, now equation 1 says that IA1 is equal to minus IA2. So we have only the positive and the negative sequence network in the combined network. And it says IA1 is equal to minus IA2. So draw the positive sequence network, then draw the negative sequence network. IA1 direction is marked, IA2 is marked. Okay, so they are coming into the same node. They are flowing into the same node. They are coming in the opposite directions and trying to converge at a point. Okay, so IA1 is equal to minus IA2. That means IA1 plus IA2 is equal to 0. So both the currents IA1 and IA2 are towards one node. Okay, and the second equation says that VA1 is equal to minus VA1 minus VA2 is equal to VA1 minus VA2 is equal to IA1 into ZF. Okay, or VA1 is equal to IA1 ZF plus VA2. Okay, that means VA1 is not equal to VA2. Okay, VA1 is equal to VA2 plus some drop across the impedance ZF. Okay, so we include the impedance ZF between the two networks. Okay, so the parallel connection of positive network and negative sequence network through the fault impedance ZF. So after drawing the combined sequence network, we have to find out the expression for IA1, IA2, VA1, VA2. Okay. Now let us find for IA1. So from this network, EA is equal to the sum of the drops. Okay. Generated EMF is equal to the sum of the drops. IA1 is at 1 plus IA1 is at F minus IA2 is at 2. Got it? EA is equal to IA1 is at 1 plus IA1 is at F minus IA2 is at 2 because the current direction of IA2 is opposite to that of IA1. Then minus IA2 is nothing but IA1. So we get EA is equal to IA1 is at 1 plus IA1 is at F plus IA1 is at 2. Okay. So we can write EA is equal to IA1 into Z1 plus Z2 plus ZF. So from this, IA1 is equal to EA divided by Z1 plus Z2 plus ZF, which is also equal to minus IA2. So now we got the expression for IA1 and IA2. So next to get VA1 and VA2. So from the sequence networks of generator, we have VA0, VA1 and VA2 expressions. So VA0 already we have seen It is 0 because IA naught is equal to 0 for a line to line fault. Okay. So VA naught is equal to 0. So let us write the expression for VA1. EA minus IA1 Z1. Okay. Substitute for IA1. So from the previous equation, from this equation, substitute for IA1. Take LCM. EA is common. This when you take LCM, this term will go to the numerator as Z1 plus Z2 plus ZF. Okay. Minus Z1 divided by Z1 plus Z2 plus ZF. So Z1 and minus Z1 gets cancelled, giving VA1 is equal to EA into Z2 plus ZF divided by Z1 plus Z2 plus ZF. Okay. So now VA2 is equal to minus Z2 into IA2. And minus IA2 is IA1. And minus IA2 is IA1. So substitute for IA1, Z2 divided by Z1 plus Z2 plus ZF. So we got the expressions for the sequence voltages also, positive and negative sequence voltages. Next step is to get the expression for fault current. So from the circuit diagram, we have seen that fault current IF is equal to IB. So from the matrix form for the current phasors in terms of its symmetrical components. Okay. So current phasors in terms of the symmetrical components. When you expand for the second row, you will get only IB. IB is equal to IA naught plus A square IA1 plus A IA2. This IA2 substitute as minus IA1. IA2 substituted as minus IA1. Take IA1 common. So A square minus A into IA1. We know A square minus A is minus J root 3 into IA1. So now to get only the magnitude of fault current, we remove minus and this J operator. So root 3 into IA1. So from the expression for IA1, substitute for IA1. So we will get the fault current. Okay. And the last step is to find out the fault current based on the nature of the neutral grounding. So for a line to line fault, we have seen that the network, equivalent network will not include the zero sequence components or the zero sequence network. Okay. Since Z0 is not in the network, the presence or absence of grounded neutral is not going to affect the fault current. Okay.